In today's lesson, we're going to continue our study of probability, where in the previous lesson, we were talking about sort of very generally how do we count up probabilities. In today's lesson, we're going to be looking at something a little bit more specific known as conditional probability. And the idea with conditional probability is that sometimes we have more information about the events that we might care about, and it's one method that we can use in order to take into account this extra information that we have. So the objectives for today's lesson are going to be to understand what conditional probability is and also how do we compute it from our non-conditional probabilities. We want to understand what's known as the multiplication rule for probability. We want to understand what's known as the law of total probability. And we also want to take a look at Bayes' theorem and sort of what it's used for. So to motivate this idea of conditional probability, we want to think about, say, the probability that it's going to rain on any given day, right? And so, of course, you could just think about, say you live in whatever city and some portion of days it rains during a certain time of the year, some portion of days it doesn't, right? And so you could use that to estimate just the probability. But what if you wake up on some morning and you look outside and you notice, oh, it's very dark clouds out there? Intuitively inside of your body, you know the chances of rain are going to be higher today than on an average day. Or if you wake up and you look out the window and you see it's bright and sunny and blue skies, not a cloud in sight, then of course the chances of rain also feel like they're going to be lower, right? And so in some sense, by looking out the window, we've updated the information that we have and the probabilities start to change. So this is the idea with conditional probabilities. How do we take into account the knowledge that we might have in order to sort of more accurately capture the probabilities that we care about? So somewhat more formally, we might want to know the probability of A when we have extra information about B. A might be the probability that it rains. B is the event that there's a cloud outside. So we can ask the question, what is the probability that A occurs given that we already know that B has occurred? Right, so what's the probability of A conditional on B occurring? We call this the conditional probability of A given B. Notationally, we're going to write this down as probability of A, and then we draw a bar, and then write the event on the other side, right? And so this is read out as the probability of A given B, or conditional on B. And everything on the left side of that bar is going to be the event that we care about. And everything on the right side of the bar is what we know to have already happened. So in essence, what we're thinking about is that when we know that B has occurred, the sample space that we care about is no longer S, right? And rather, it's going to be B, right? And so by way of example here, you can think about what is the probability that a randomly selected card is going to be the ace of spades, right? If we have a deck of 52 cards, right? And of course, if we think about our counting probabilities from last time, well, there's only one way that we could draw the ace of spades. There are 52 possible cards, right? And so it's going to be 1 out of 52. But what if we had more information, right? So what if we know that we drew out this card and we know that the card that we drew out is just going to be black, right? Well, we're no longer thinking that there's 52 possible cards, right? We still know there's only one ace of spades, but there's not 52 cards that the card we're holding could be. Instead, because we know it's black, there's only going to be 26 possible cards. And so in essence, what we've done is we've said the sample space is no longer size 52, it's now going to be sample size of 26, right? And so we're 1 over 26 now. What if we know that the selected card was going to be an ace, right? So we drew out a card and someone tells us it's an ace, and we want to know, given that this is an ace, what's the probability that it's the ace of spades? Well, now the relevant sample space is not 52 cards, but it's only 4 cards, right? And so because it's now only 4 cards, we're going to say that n is equal to 4. Probabilities 1 in 4. And you could also think about, what if I told you that it was a black ace? Well, now we know it's either the ace of spades or the ace of clubs, right? And so sample space has become 2 items large. So it'd be 1/2, right? And so by conditioning on B, essentially what we're doing is we're shrinking down the relevant sample space. And that's how you can think about sort of integrating the knowledge that we have about the situation. We can sort of write down formulaically how would we compute the conditional probability. And so the probability of A given B is going to be this joint probability, the probability of A intersect B, the probability of A and B, divided by the probability of B. And if you think about it, this formula is really just capturing that idea, right? Because if we know that B has happened, then what we want to know is how many ways can A still happen when B has also happened, right? So how many ways are there of both A and B happening? And then instead of dividing by the probability of the whole sample space, we're just dividing by probability that B has occurred. So in other words, what's the portion of times that both A and B occurs out of the total time that B occurs? Now, if the event has probability 0, if probability that B occurs is 0, then we don't define this probability here, right? We say it's undefined, and that would be because we're dividing by 0. But also, in some sense, you could think about this as sort of not being a super intuitive notion, right? If I say, we're rolling a 6-sided die, what's the probability that it's, a certain value given that it is, larger than 25? Well, we can't roll larger than 25, right? So probability is going to be 0. That's not really part of the sample space anyways. We relax this idea a little bit when we start dealing with sort of more complex variables, but for now, if the event's undefined, we can't really condition on it. We could have never observed it. We can also rearrange this formula for what's known as the multiplication rule, right? So the probability of A and B, if you just multiply both sides of this equation by the probability of B, is given by probability of A given B times by probability of B. Now, of course, you could change B and A there, right? So it could also be B given A times by the probability of A. It's going to be the same thing. And so this is known as the multiplication rule, and it's probably the most commonly used way of computing this joint probability of A and B. Now, we can extend out this multiplication rule into what's known as the law of total probability. And so the idea is that we want to think about partitioning up our state space, right? So if we take our set S of all of the different possible outcomes and we divide it into a set of k different events, and the idea is that each of these events should be disjoint from one another, right? So there's no overlap between them, but also the events should cover the whole space, right? So we want it so that if you take the union of all of the different AJs, you get the sample space back, but any two of them are going to be disjoint from one another, right? And so you could think about if we're drawing cards, one way you could partition it is to take the different suits, or you could take the different face values, or you could take each card individually, right? So you can sort of break it up in any number of different partitions, but a partition simply divides the space up in a way that includes every element, but there's no overlap between. Then if we use the multiplication rule, we can see that the probability of, say, some event B and any one of those event A's happening is given by the probability of B given AJ times by the probability of AJ, right? And it turns out that if we do this across the whole partition, this is one way of us computing the probability of B, right? So sort of in full, if we want to know the probability of B, we can partition the whole sample space into sets AJ, and then we can sum up from j equals 1 to k using the multiplication rule to write the probability of A and B, or AJ and B. We call this the law of total probability. And basically what we're thinking about with this is that sometimes it's really easy to compute a conditional probability where it's really hard to compute the non-conditional probability, right? So sometimes if I give you one little bit of piece of information, then it's going to be quite easy to know what the probability is. And if you don't have the piece of information, it's going to be a lot harder to work out, right? So let's say that I'm flipping a coin a bunch of times, and I want to know the probability that the number of heads in the first 10 tosses is exactly 5, right? Well, if I know how many heads I had after 9 tosses, that becomes a much easier probability to think about, right? So if I know that I had 1, 2, 3 tosses on the first, well, the probability that I end up with 5 after the 10th toss is going to be 0, right? Because I can only get one more head. If I have 4, well, then in 1/2 of the time, I'm going to end up with 5. If I have 5, in 1/2 of the time, I'm going to end up with 5. And then every other possibility, I'm going to be 0 again, right? And so you could think about this where sort of conditioning on how many heads there are after 9 tosses makes that a lot easier of a probability to compute. And in this case, the only issue that you're going to have is then computing probability that there are exactly 4 after 9. But you could sort of repeat this process down and end up computing this probability here, right? And so there's going to be times where extra information makes this easier. This becomes a very useful tool for computing the different marginal probabilities. When we're talking about marginal probabilities, just to clarify, the probability of an event by itself is known as the marginal probability. This is used in contrast to conditional probabilities, right? So we have marginal probability is the probability that B happens. Conditional probability is the probability that B happens given we know something about A. Now we can combine these different results together to give what's known as Bayes' theorem. Bayes' theorem is probably the most famous result in all of probability. And it's this handy little formula. And basically what this formula is going to do is let us move from information about A given B to information about B given A, right? So we can write down this formula and we can say that the probability of B given A is equal to the probability of A given B times by the probability of B divided by the probability of A, right? And you can work out why this has to be the case just by using our multiplication rule, right? And the second equality that we have there replaces probability of A in the denominator with that law of total probability. Because oftentimes when we're going to be trying to apply Bayes' theorem, we're going to want to use that partition breakdown trick. Right, so when might we use this? Well, let's say that you go in to your doctor and they run a medical test testing for some rare disease and the test comes back positive, right? And so you want to know what's the probability that I have this disease, call that event B, given I tested positive, call that event A, right? And, perhaps this isn't, seems like an obvious question to answer, but normally what we actually know about is what's the probability that the event or that the test comes back positive if you have the disease, right? A test might be 99% accurate. So we know that for people who have the disease, 99% of the time, it comes back with a positive result, right? But what if the disease is super rare in the population, right? So we have, it's 99% accurate, but only 1 in a million people actually have this disease. Well, even if you're thinking that the test is quite accurate, because the disease is so rare, it might be the case that you just have a false positive, right? And so we could use this Bayes' theorem here in order to go from the accuracy of the test to how likely is it that you actually have the disease. And importantly, those are not going to be the same probability, at least not in general, right? In this case, we can also see why the law of total probability might be handy here, right? So if we're thinking about this, B is the event that you have the disease. A is the event that the test comes back positive, right? And so if you want to just know what's the probability that the test comes back positive, well, this feels like it might be easier to know what's the probability that it comes back positive if someone has the disease, and what's the probability that it comes back positive if someone doesn't have the disease. So how accurate is it? But then how often do you get sort of false positives, right? And so if you can fill in those two values, you can write out our denominator here, and we could actually work through and compute what this probability is going to be. So, for instance, how likely is it if you have a rare disease if you're going to be testing for it? Another common example where you might try to apply Bayes' theorem here is if you have emails detected as spam, and you want to know how likely is an email to be spam given that it was detected as spam by the filter, right? And so it's a similar concept here, but we know that some amount of spam that's detected by the filter is not going to really be spam, right? And so you can fill in sort of all of the different values there and see. And I might encourage you to take a look and say, if you have a 99% accurate test and there's only a 1% chance that it sort of makes a false positive, but in the population, only 1 in a million people actually have this disease, to calculate what's the probability that a positive test means that you have the disease. And I think that the result might be a little bit surprising to do, but I think it's a handy exercise to actually work through and see why are those two values so different from one another. That's essentially everything that I wanted to talk about today. So just to summarize, conditional probabilities allow us to take extra information in that we know in order to update the chances that we think an event will happen. From conditional probabilities, we can get the multiplication rule, and from the multiplication rule, we can get the law of total probability. Those tools help us to compute marginal or non-conditional probabilities. Our Bayes theorem is going to allow us to update our view about the world by switching which conditional probabilities that we're talking about. So we combine conditional probabilities and the multiplication rule, and that allows us to switch from probability of A given B to the probability of B given A. So with all of that, we're going to continue exploring probability in more depth in the next lecture, and I hope that I will see everyone there.